Match problem 4 is a little bit different. This problem isn't about continuity itself. Instead, it's a problem that we're going to use the idea of continuity, and another theorem that we'll introduce, to solve this inequality. So we want to know, when is this rational function less than 0? So before we get into anything with continuity, we're going to look for what are called partition numbers. So partition numbers are numbers where the function is either equal to 0 or undefined. So if we're considering where our function is equal to 0, we only need to consider zeros in the numerator. So when will x squared minus 1 be equal to 0? So factoring x squared minus 1 would give us x minus 1, x plus 1 equal to 0, which would be true whenever x equals 1 or x equals negative 1. To consider where our function would be undefined, we need to look for zeros in the denominator. So we need to solve for, when would x minus 3 be equal to 0? And in this case, that would be when x is equal to 3. So our partition numbers that we need to consider here are x equals 1, x equals negative 1, and x equals 3. We'll come back to what we need those partition numbers for in just a second. But first, let's introduce another theorem. So the sign properties on an interval states that if f is continuous, on some open interval a to b, and our function value is never equal to 0 for all values of x on that interval from a to b, then either our function value is strictly positive or strictly negative. So our function value has to always be greater than 0 or always less than 0 on that interval from a to b. So what we're saying, we could look at a couple of different examples here. If we choose some interval from a to b on each of these graphs, in our first graph, let's assume that our function is continuous on this interval from a to b. Our function value can never equal 0, and our function starts somewhere above the x-axis. So in that case, our function can do whatever it wants, change directions, head up and down. We can get really, really close to that value of x equals 0, or our function value equal to 0, but we can never cross the x-axis itself. So if our function value can never be equal to 0, there's no way to cross into negative values. Same thing if we started off with a function that was negative. We could get really, really close to a function value of 0, really close to that x-axis, but never cross it because our function can't be equal to 0. Our function value can't be equal to 0. So our function has to stay negative if it starts negative. So we can take advantage of that theorem to construct a sign chart and use that sign chart to solve our inequality. So for a sign chart, we just draw a horizontal line and let that represent the values of our function f of x. And we're going to start by indicating these partition points that we found. So we know that at -1, our function is equal to 0. At 1, our function is equal to 0. And at 3, our function is undefined. So I'm just going to distinguish that from a 0. Our function is not equal to 0 here. It's undefined. So if we look at some particular interval here, say from -1 to 1, nowhere in that interval is our function equal to 0. So our function can't switch between positive and negative. So in each of these open intervals, we just need to choose some test point, any value that's in between those partition numbers, and determine what's our function value at negative 2, 0, 2, and 4 to determine whether that's negative or positive. So we could start with f of negative 2. We would plug that back into our original function, and that would give us negative 3/5, which in this case is less than 0. So for all values of x less than negative 1, our function value has to be negative. Then we would consider f of 0, our next test point. This would give us positive 1/3, which is greater than 0. So everywhere in the interval from negative 1 to 1, our function has to be strictly positive. Our next test point would be f of 2, which would give us a function value of negative 3, which is, again, less than 0. So from x equals 1 to x equals 3, our function is taking on negative values. And then our last test point to consider would be f of 4 is going to give us a function value of 15, which is obviously greater than 0. So for values of x equal to 3 or larger, our function is going to take on positive values. So the original problem was asking us to find when is x squared minus 1 over x minus 3 less than 0. So when is it negative? So we have this interval from negative infinity to negative 1, and another interval from 1 to 3. So we can say that this function is less than 0 for x less than negative 1 and 1 less than x less than 3. So if x is less than 1, our function is negative. If x is between 1 and 3, our function is also negative. Or if we were to write this in interval notation, that would be negative infinity to 1, union 1 to 3.